Welcome to another edition of Comet Algebra. This video is for Algebra 2, Chapter 5, Section 5, about complex numbers. So first, to define what a complex number is. It's a number that has two parts, really. It has a real part and an imaginary part. The real part is just a regular number. They call that A. And the part that's imaginary usually has a number in front of it, B. And of course, I is defined to be the square root of -1. Imaginary numbers exist outside the realm of real numbers. So back in Algebra 1, when you had a Venn diagram, a box representing the real numbers that was divided into irrational and rational, these imaginaries are outside of that. And they can be written like this. They might look like 4 minus 3i. That's how we write a complex number. It has a real part and an imaginary part. And these are graphed on a different plane other than the xy plane. They're graphed on the complex plane. And this r really should be written as that fancy r with the double that stands for the real numbers. This horizontal axis is for the real part of the number, and this vertical axis, this I, is for the imaginary part of the number. So let's do some graphing here with some of these. If I were to go ahead and graph this 4 minus 3i, so the horizontal, the real axis is the 4, so we would go to the right, 1, 2, 3, 4, and then the -3i, the imaginary part, is going down 1, 2, 3, and so right here, this point is 4 minus 3i. So it's really similar to the xy, but we just have a real axis and then an imaginary axis. Another quick example, if we were asked to graph -2 plus 4i, so we would go in the negative direction on the real axis 2, and we'd go up 4, 2, 3, 4, and that would graph right there. Come on, there we go, -2 plus 4i. I'd like to add a definition now, and in our discussion with this graph, when we are asked to find the absolute value of a complex number, it's really defined the same way that we defined absolute values way back when we learned that we were just taking the positive value of it. The absolute value, by definition, is how far that number is from 0. So the absolute value of a complex number, once again, is the distance that it is from the origin, 0, 0. So if I were to draw in the absolute value of this 4 minus 3i example, I would draw in a line from the origin to that point. So this distance is the absolute value. And if we were asked to find this, we could do so by using the Pythagorean theorem. So if we go ahead and make a triangle with this x-axis, I'll draw on the triangle here. The distance of this leg, the length of this leg of the triangle, is 4. And again, since we're talking distance, this distance is 3. And then we're asked to find x being the absolute value of 4 minus 3i. And I hope you noticed that I was ignoring the -3 here because it is a distance. So to find this x being the absolute value of 4 minus 3i, we use Pythagorean theorem. We have that x squared equals 4 squared plus 3 squared. And so if we square 416 plus 9 is 25, and so I have x squared is 25. Therefore, x is 5. So we can say the absolute value of 4 minus 3i is 5. So once again, absolute value is the distance from the origin, and we find that distance by using good old Pythagorean theorem. So let's look at a different example. We're asked to graph 4 minus 2i and find its absolute value. So 4 is positive, so we go 4 units in the positive direction. The 2 is negative, so we go down 2, and I'll put the dot here. So right here is 4 minus 2I. And now I'm going to draw in the distance from the origin to that point and make the triangle. So this is our x, and we're asked to find that with Pythagoras. This distance is 4, this distance is 2. So I have x squared equals 4 squared plus 2 squared. X squared equals 16 plus 4. So x squared is 20. X is the square root of 20. Now you'll notice I did not put plus minus. We are finding a distance. We are only interested in the positive root here. But as usual, we can simplify this. We notice that it has a 4 in it, 4 times 5. So x becomes 2 square root 5, which is defined to be the absolute value of that imaginary number. Next, we're going to have a discussion about when we're adding and subtracting these complex numbers, and also when we're multiplying them. So when you add them, you combine the real parts together, and you combine the imaginary parts together. It's very much like when you learned how to combine like terms. So this negative sign is being distributed, remember? So I do have 5 minus 2, which is 3. And then I have negative 3i minus 6i, which is negative 9i. And that's all you can do, so you're done. However, when you're multiplying them, before we begin example 3, I just want to remind you of something. I want you to remember that I squared is equal to negative 1. So when we're done with all this, the highest power of the I we should ever have is I to the first power. If we have I squared, we would be doing this substitution, or any other higher power, I to the third, I to the fourth. You still do this substitution to bring it down. So let's see what that looks like. Let's go ahead and FOIL this. So 4 times 2 is 8. 4 times 3i is 12i. The inner product is negative 4i, and the last times the last is negative 6i squared. Again, we can combine like terms, and then we're going to do that substitution. We're going to remove the I squared and put in the negative 1. So then we have 8, and 12 take away 4 is 8i, and I have negative 6 times negative 1, so that becomes positive 6. And then you can go ahead and combine the 8 and 6 is 14, and then we have 14 plus 8i. Okay, a definition here that we have had already once this year, but it bears repeating. Conjugates are algebraic expression of the form a plus b, a minus b. Whatever the binomial is, the conjugate has the other sign, the plus or the minus. So, of course, we can have complex conjugates. If we have a plus bi, its conjugate is a minus bi. And what that could look like is, what if we're asked the conjugate of 5 minus square root 2 times I? Then the conjugate of that would be 5 plus the square root of 2 times I. And I guess I had told you that usually we write the I in front of the radical, so I should learn to be consistent and do that. Anyway, just reviewing what conjugates are. So you need to know how to multiply both regular conjugates, which you've learned already, and complex conjugates. So let's just take a look at this. So if you FOIL this, you already know that you'd have a squared, and you'd have a plus ab, and a minus ab, and then a minus b squared. So when you simplify this, it just becomes a squared minus b squared. And this we learned forward and backward when we were reviewing factoring, when we factored the difference of two perfect squares. So now let's look at multiplying complex conjugates. Again, first times first is a squared. The outer product is a minus abi. The inner product is a plus abi. And the last times the last we'll have to follow and see what happens here. At first, it's a minus b squared I squared. But remember, I squared is negative 1. So these two middle terms subtract away, just like in the regular conjugates. But when we do the negative 1 substitution right here, negative 1 times negative b squared becomes positive b squared. So now if you look at what we have here, this is the difference of two perfect squares, and this is the sum of two perfect squares. So remember how you couldn't factor them before? Well, you can now. So what I mean is, before we could factor this, it was the difference of two perfect squares. It factored into x minus 4 and x plus 4. And we learned that a long time ago in Algebra 1, no big deal. But now, when we have x squared plus 16, now we can factor this. Because, just refer back here, let me just see if I can slide it. Because it's a perfect square here, plus a perfect square, which is what we have here. And let's just take a look at what it's going to look like. This is going to factor into two complex conjugates. And the only thing that's different about complex conjugates is they have an I in them. So in the same way this factored into x minus 4, x plus 4, this would factor into x minus 4i and x plus 4i. And now just try foiling that back and make sure you agree and understand that when you FOIL these two complex conjugates, you're going to get x squared plus 16. So kind of play around with that and just realize now you have been able to factor. It's expanded our factoring capabilities from the difference of two perfect squares to the sum of two perfect squares. We have one concept left to cover in this section. The goal of looking at this next part is to be able to simplify if we have, let's say we have I to the 387th power, and we need to simplify that down. Now, I don't know about you, but I don't want to try to figure out how many I squareds are in there. That would be a pain. So what we're going to do is look at the powers of I and see if we can find a pattern. So take a moment, write this down, and then start filling in the answers based on your knowledge that I squared is negative 1, and I'll do the same, and let's see if we can see the pattern. So it starts that I to the first is just I squared is negative 1. We can break I to the third down, break that down into I times I squared, which is negative 1 times I, which is negative I. Let's break I to the fourth down to I squared times I squared, which is negative 1 times negative 1, which is positive 1. All right, so far no pattern, is we just have I, then negative 1, then negative I, then positive 1. So keep going now. Break down I to the fifth into I to the fourth times I, and figure that out. And then pause the video and keep going by yourself for a moment. Okay, so if you've had time to fill in some more of these, and let's start observing the pattern. I, negative 1, negative I, positive 1. I, negative 1, negative I, positive 1. There seems to be 4 answers that are repeating over and over again. And this would hold true no matter how high you went. So we need to kind of describe this pattern. Since it's a repeat of 4, and we want to find, I'm just going to make up a problem here. Let's say we want to find what I to the 243rd power is. And we don't want to write this all out until we get to 243. We see that this is a repeating pattern of 4. So if we divide by 4 and look at the remainder, we can kind of write down the results of this pattern. So, like, let's just take I to the 4th, for instance. if you divide I to the fourth by 4, you don't have a remainder at all. Let's focus on the remainder. So if we divide the exponent by 4 and then observe the remainder, if the remainder is 0, the answer, okay, like 4 divided by 4 is even, so it's 1. 8 divided by 4 is even, so that's 1. The answer is 1, which we notice here in my I to the 4th and my I to the 8th and my I to the 12th. Whenever it divides evenly, the answer is 1. So what if we divide on our calculator and the remainder is 0.25 or 1/4? That would be like if you divide 5 by 4, you'd have a remainder of 1. So right here is the remainder of 1. Right here is the remainder of 1. So when there's a remainder of 1 or 0.25, the answer is I. Likewise, if the remainder is 2, or in your calc that shows up to be 0.5 if you punch that in, then the answer would always be a -1. And if the remainder on your calc, it shows 0.75, if you were doing the division problem, it would show as a remainder of 3, then the answer is -I. It always has to be one of these 4 answers. And so if we take 243 and you punch that out on your calculator, you divide it by 4, we get 60.75. Therefore, I to the 243 power is -I. It's always going to be one of those 4 answers depending on the remainder. All right, I think we have everything we need now to do section 5.5, so have fun with math.